Hi, I'm Klaus-Jørgen Christensen, and this is the presentation I gave at the ISRA, International Symposium on Room Acoustics, 2013 in Toronto, Canada. It's co-authored with my colleagues George Koutsaris and Jens Holger Rendel, and we are from Odeon AS. So the Odeon software has long been about simulating room acoustics, and in the latest version 12 of Odeon, we've also included the ability to measure room acoustic parameters in Odeon. So this is what it's all about. So the contents of the presentation is simulations and measurements, creating reproducible measurements, some studies, signal-to-noise ratios and their relationship to the predicted T30 reparation time, using different excitation signals, sensitivity to position, and 2 examples, 2 case stories, an auditorium and a cathedral, and finally conclusions. So, simulations in Odeon. Odeon uses a hybrid calculation method, which is based on the image source method and a ray radiosity method using laid rays. It's an energy-based method, so it excludes phase. Wave phenomena are approximated using scattering and diffraction algorithms, and the sum of reflections is put into histograms, and from those histograms we derive the ISO 3382 parameters in accordance with Part 1, Part 2 and Part 3 of the ISO standard. So on measurements, we obtain an impulse response using Odeon. Using an impulse signal, you can use the sweep method, or you can also use a start gun hand clap popping of a balloon and record it with a recording software for later analysis in Odeon. Then we derive the ISO 3382 parameters, and in the implementation of Odeon, our aims has been to make the implementation automatic, to create reproducible results and give warnings when needed. So, what about simulations? There are some strong points actually with simulations, even though you might think that this is a crude representation of the real world. In simulations we do have a perfect omnidirectional source. We do have a perfect direct signal, direct excitation. We have a well-defined source power, it's mathematically defined. We have no background noise. We have perfect directivity of the microphones. They're simulated. And we have octave bands in terms of energy, so we don't need any filtering. We get no ringing from digital filtering, no time smearing. And of course, simulations is extremely useful for predictions. Measurements, of course, do have strong points because they include wave phenomena, they fully include the geometry of the room, and they fully include wall properties, so absorption and scattering. And this is very useful for investigation and documentation of real world rooms. So what have we done in order to make the measurement system supply reproducible results? 2 problems we have. The first is the onset time of the impulse response. So when you measure an impulse response, you might get a wrong impulse response, a fake impulse response due to impulsive background noise before the actual impulse, and this can give wrong results for parameters such as clarity and gravity time and so on. So we made an algorithm that's robust and will automatically detect the correct onset time of the impulse response and discard of this part of the impulse response. So this is not what Odeon does, and this is what Odeon will do. Here we see the squared impulse response and the detection of the onset time of the impulse response. And again, here we see the derived energy curves, the decay curves, and with wrong onset time we would get a reparation time of 1.91 seconds, and that's actually the same with correct onset time. But when we look at other parameters such as EDT and clarity, you can see here that with the wrong detection of onset time we'll get completely wrong EDT, and in particular clarity is way out of range. Whereas here we have the correct onset time and the correct parameters. So this is extremely important for these time interval parameters like clarity, for example. So this is not what ODN does, and this is what ODN does. And thereby we are much more likely to get reproducible and trustworthy results. The other problem with the analysis of the measured impulse response is that there is a truncation time for the impulse response. At some point, the measurement will reach the point where the impulse response runs into the background noise, the noise floor. And we need a reproducible way to detect this noise floor and when we should truncate the impulse response. We have used the method proposed by Lundeby, where there's an iteration process used in order to find the truncation time. And this happens automatically. Again, we'll look into what happens if you have a wrong detection of the truncation time of the impulse response. So here we have wrong detection. We don't detect the impulse response, and on the right side you see that we have detected the impulse response and we have an estimate of the noise floor. Here we see what will happen if we didn't truncate the impulse response at the correct place. We get a reverberation time of more than 10.6 seconds, and the correct result in this case would be 1.9 seconds. So it's dramatical changes. Of course, this is exaggerated a lot, but the problem is actually more important and more fatal if it's smaller differences where you'll not notice that there is an obvious error. So you could easily get a result of maybe 2.2 seconds or 2.5 seconds here without it being very obvious on the decay curve that this is a wrong result. So this is done automatically in ODN. Truncation of the impulse responses should also occur before you get any impulsive noise following after the valid part of the impulse response. And in this case we see that ODN have detected the correct truncation point anyhow. And we get a decent estimate of the decay curve. In some cases this is not possible because the measured impulse response is polluted with impulsive noise, and you can see over here there is a kind of a shoulder in the decay, and again we have an impulsive background noise here. In that case ODN will give a warning in the title bar of the measuring display saying that the nonlinearity parameter is high in this case, and if it's higher than 10 out of 1,000, then you'll get a warning. This is a parameter suggested as a quality criterion in the ISO standard. So in some cases ODN will not be able to give a reliable result, but it will try to give a warning if the decay is nonlinear, strongly nonlinear, or if we don't have a sufficient decay range, you will also get a warning, so if there's not sufficient background signal to noise level. We have estimated the truncation point, and we also estimated the level of the background noise. So we have two things we can compensate for. We can truncate at the noise floor, and we can add a truncated energy compensation for the truncated energy at the end of the valid part of the decay curve. And in fact we can also compensate for the noise floor by subtracting the noise floor at the valid part of the impulse response. Having both automatically detected the onset and the truncation time, ODN can even pick out a part of multiple impulse responses and derive a valid decay curve. In this case we have a series of hand clap, and ODN picked the best one, giving the best estimate of the decay curve. So this can be used for sketch-like measurements. You go to some room, and while you take some pictures you might as well record a few hand claps in the room and bring them home. This is not a very precise measurement of course, but it can give you a good good rough estimate of what is the reverberation time and so on in this room. Better than nothing. Here we see the squared impulse response again, and we have the onset time detected by ODIN, and we have the truncation time. And as you can see, that ODIN picked the best of the impulse responses in this recording. So you can load a WAV file into ODIN and get a result like this. We have two case studies here, an auditorium at the Technical University of Denmark. You see that we have modeled tables and stairs in the room, and we found in this case that it gave slightly better agreement between simulations and measurements when we did model details like this in the room. So we do recommend this. In this room, the tables are of hard wood and quite reflective, and therefore it's more important that these details are included in the room. So it's a fairly small auditorium, and it has a reverberation time of 1.9 seconds at 1000 Hertz. And it's supposed to be used for speech, but it's really not a well-defined, designed auditorium. The other room is to try out the extent of the stability of the measurement software. It's a huge cathedral-like room, Hagia Sophia in Istanbul in Turkey. It has a volume of almost 230,000 cubic meters and reverberation time close to 10 seconds. And it's a lot of coupled spaces, and in most of the measuring positions, direct sound from the source to the receiver is not available. So it's a real challenge for measurements. So this is where we compared what happened if we measure reverberation time with different signal-to-noise ratio. So the sweep length, each time we double the sweep length, we increase the signal-to-noise ratio by approximately 3 decibel. We tried to see what will be the derived reverberation time if we do not compensate for truncation or noise floor, and what happens if we do compensate for truncation and for truncation plus noise floor. As you'll see, if you do not compensate for the truncation, you'll be able to derive reverberation time even with very poor signal-to-noise ratio. And this is actually something bad, because it allows you to derive reverberation times that is much too low compared to what it actually should be. So they will be wrong due to poor signal-to-noise ratio and no compensation for truncation. If we do compensate for the truncation, there's a tendency that reverberation time estimated will be too long if we don't have a almost perfect signal-to-noise ratio. And when we compensate for the noise floor by subtracting the noise floor from the valid part of the impulse response, we converge towards the correct result much faster. And results here in this region would be okay for most people. So reproducibility with respect to receiver positions, we tried 7 positions with small changes to the original position here in receiver position 5. So just moving 0.3 meters to the left and right, and 0.2 meters forth and back, and 0.1 meter up and down, to see how much does the result change. There's 2 points in this. One is does the measuring software provide reliable and reproducible result? The other is, can we say that these ISO 3382 parameters are reproducible, like if you come back and measure the same measurement later on at a slightly different position. You can't position your microphone completely exactly the same position. Well, will you get a result that is more or less similar? So here we see a few examples on the parameters for these 7 positions, and as you can see, for simulations it's almost the same result. And as we'll see later on, we do see different results when we change position to other locations in the room. So this is just that when you are very close to the same position, you will estimate almost the same simulated result. For measurements, we see that at lower frequencies, the deviation between different positions do get high, and that's probably because we have modes in the real room which is not included in the simulation. Whether this is actually an advantage or not is debatable. Anyway, when we are up at 500 to 1000 Hertz, there's quite good agreement between the different slightly changed measurement positions. Here we see T30, and the results in all these 7 positions are almost similar for measurements as well as simulations. So they agree that T30 is probably a pretty stable number in a room that is not very non-diffuse. SPL, we'll see that up here we have a deviation less than 1 decibel, so we can say this is also quite reproducible. At lower frequencies we do see some increase of the error, which is expected because there's modes in the measurements. For simulations it's very stable results we get. Gravity time, I'll not go much more into that. And then T50, again we have a very stable result, and there's quite good agreement between measurements and simulations. Differences for all parameters are about from 500 and up are within 0.5 just noticeable differences, so we can say there's quite good agreement. So we also tried a few different excitation signals. We tried balloons and hand claps and sweep, and the sweep is taken as a reference here because it has a very good signal to noise ratio, so you can consider these are the true results. For hand claps we're not able to derive reverberation time parameters, and that is because there was too poor signal to noise ratio, so that's how it goes. For a balloon and sweep, there's very good agreement between reverberation time parameters. T30 in particular is in very good agreement, and you can say that you might just as well use a balloon as the sweep method. Clarity and definition are not way off. They are in fair agreement, but the sweep method is the reference here because we have a better omnidirectional source with the electroacoustic system used with the sweep method at dodecahedron, and for high quality measurements this is the method to use. And then the case study on the Auditorium 26. I will not go much into the numbers, but you can see that we do see the variation with position for EDT. The measurement and simulation agree that reverberation time is fairly stable with position. It doesn't vary much with position. SPL, of course, it varies with the distance, and clarity does also vary with the position, and there is very good agreement between measurement and simulations. For the large cathedral-like room, Hagia Sophia in Istanbul, we see that variation with position is in very good agreement, in quite good agreement. There is some bigger deviations of 4 decibel almost in clarity down here, and that is to be remembered that we have also a very big variation, much bigger variation in clarity here than you would see in a normal room, more than 20 decibel, which is not what you see in an auditorium, so that we still have fairly good agreement, and you can see the variation with position is quite satisfactory. That also goes for gravity time. You have to keep in mind that a measure like clarity is probably not valid at all in this type of room because the build-up of the squared impulse response in remote positions takes more than a second, and clarity takes into account in particular the first 80 milliseconds of the impulse response, so it's probably not reliable or valid or meaningful results that clarity provides here. Still, it's nice to see that measurement and simulations agree. So, conclusion for this presentation is that we have an implementation of the measuring system in Nodian that has automatic detection of onset and truncation time of measured impulse response. We have compensation for the truncation and for the noise floor of the impulse response. The non-linearity parameter Z pinpoints suspicious impulse responses. And the ISO 32 parameters creates reproducible results with small changes in position. And high agreement between simulation and measurements is possible. Thank you very much.